Yeah. One of them says math team. So you can, I think on the left one. The left's the one that's a math team one. Okay, thank you. Let's see. Okay, so page 3, we have graph of f that consists of line segments and a semicircle. So you have line segment, semicircle. As shown, g of x is the definite integral from -2 to x of f of t. So this is a relationship here. We can instantly tell what that relationship is. Okay, this f is sitting at the derivative level of g, right? Because it takes an integral for f to rise up to the same level as g. So that means f must be sitting at a g prime level. Okay, so we're looking at f graph, but we also know this f graph is the g prime graph. Right. All of these problems are going to be in reference to g, so we need to be able to connect what's the connection, what's the relationship between g and f, right? And we gotta make that clear. So we know g is the definite integral from -2 to x to f of t, which means that g prime must be f of x, right? And we have established that, right? G prime is the f graph. And if I want to find g double prime, then f is going to also go down to what? To f prime, right? We're just letting, they're both, f and g are kind of staggered in terms of their naming convention. And so once one goes down, we just bring the other one down along with it. Okay, so here's our relationship we're going to build. We have g of x is the definite integral of f, g prime is the f graph, and g double prime is f prime. Okay, so starting with part A, find g of 2. So to find g of 2, we see that this is the definition for g. So all we do is replace every x we see with 2. So now we know what to do. We know that we're going to be involving the graph. We're going to be involving the region between the graph and the x-axis. And between -2 and 2, we're only ever looking at the region between the graph and the x-axis. Okay, so here's the graph and the x-axis between -2 and 2. Okay, so that's a semicircle. Formula is 1/2 pi r squared. Okay, what's the radius of the semicircle? 2, yeah, from the center to a point on the semicircle, 2. So 1/2 pi 2 squared, which gives us 4 over 2 pi, which is 2 pi. Is there any adjustment we have to make, or can we just say it's 2 pi? Right. Where is this located? Yeah, located below the x-axis, right? So definite integral, you have to account for the fact that, oh, these are accumulations of negative y values. So definite integral is going to give us -2 pi. Okay, g of -4. Again, we always go back to our definition. Okay, so between -2 and -4, we see that we are dealing with this region, but anytime we're trying to read a graph, what would we prefer in terms of our bounds? Yeah, if we're doing power rule, then it doesn't really matter. You can just plug in the upper bound, lower bound, and we don't really care which one is higher, which one is lower. But if we're trying to read a graph, we prefer to read a graph from smaller to larger, from left to right, basically, right? If you're reading from right to left, you got to change everything upside down in your head, and it just makes it harder. So I like to flip the bounds. Okay, so if I flip the bounds, so I can ensure that my lower bound is a smaller value and my upper bound is a higher value. But if I flip the bounds, I got to pull a negative outside. Okay, so -4 to -2. Now we have included not only -2 pi, but we also have a triangle as well, which is also below the x-axis. And we know that the region is -1, right? 1/2 base times height. So -1 minus 2 pi. But then we got to keep track of the negative in front. I'm sorry. Not 2, -4 to -2, right? Sorry, -4, -2. So just this region here. Okay, so just negative of a -1, which is equal to 1. Okay, are we okay with that? Okay, we got the -1 because of this triangle here. Right, it's below the x-axis. This region is below the x-axis. So it's 1/2 base times height, but then we have to adjust for the fact that it's negative. But then the depth integral is negative, but then we adjusted the bounds to be negative as well. So we have two negatives, which gives us positive. Okay, part C, g of 6. Again, we always go back to our definition. So -2 to 6. Now we're going to be involving the semicircle and the triangle on the right. Okay, we know the semicircle is -2 pi. And now we got to figure out this triangle here. 2, 3, 4, 1/2 base times height, which is equal to 4. Right? This is 2 and 2. -pi and -pi. So -2 pi plus 4. Any questions there? Part D, find g prime of 4. So g prime of 4, we go back, we look to see, okay, do we have something for g prime of 4? We do. G prime of 4 is equal to f of 4. And f of 4 is just looking for the y value of the f graph at 4, and we see that y value is 2. Okay, g prime of -2, g prime of -2 is f of 2. And f of 2 is just that order pair, y value 0. Okay, g double prime of 5 is equal to f prime of 5. And f prime of 5 is sitting over here. Well, the f of 5 is here, but what is f prime of 5 asking for us to find? Yeah, not the point, but the slope, right? The derivative is a straight line, so we can find the slope here. I can pick any 2 points and just do rise over run. Down 2 over 2, this is a slope of -1, right? Okay, part G, for what value is our G function increasing? So remember, this is the G prime graph right here. So essentially, you are looking at the derivative graph. Okay, so I like to label what I'm looking at here. Anything above the x-axis is positive slope of the G graph. Anything below the x-axis is where my G graph is going to experience negative slope. Anything on the x-axis is where my original G graph is going to have slope 0. So I like to create my sign line so I can have a picture as to, because this is not the picture of the G graph, right? This is the G prime graph. So here's my G graph sign line here. I'm going to go from -4 to 6. Critical points where slope is 0. So I'll pull this -2 and 2. Between -4 and -2, we see that this is below the x-axis, right? So it's going to be negative slope. Between -2 and 2, still in this negative region here. And between 2 and 6, above the x-axis. So where is G increasing? We can just look at the arrows now. The arrow is going to tell us increasing is between 2 and 6 because G prime is greater than 0. Okay, for what value is G decreasing? Okay, we'll have a union here, so -4 to -2, and then we pick up from -2 to 2. Okay, find the x values of all points of inflection. So we know that if we're looking at the derivative graph, the points of inflection are going to come from the peaks and valleys of the derivative graph, right? So -2, 0, and 4. I'll just create a second derivative sign line just so I can see everything in front of me, so we can just have extra practice as to how to fill out a second derivative sign line from a derivative graph. And then if we look at where the graph is rising and falling, that's going to correlate with concavity, right? So here, the positive slope of my G prime graph is positive slope, so we know this is concave up, concave down, concave up, concave down. Okay, points of inflection at -2, 0, and 4 because G double prime changes signs. Okay, part J, find absolute extrema. Absolute extrema is EVT. Extreme value theorem says, look at your slope sign line and pick out all the endpoints and relative max, relative min. So the only points that we really care about are -4 and 6 and 2. We don't care about -2 because -2 is a critical point, but it's not a relative max, relative min. So only have to test 3 points here. I think we found most of it above already. Right? If we didn't, we'll just go back to our definition and just total the values up. But we see G of 6 is -2 pi plus 4. G of 2 is -2 pi. And G of -4 is 1. This is around -6. This is around -2. So between these three values, we see the highest y value is going to be 1, and lowest y value will be negative 2 pi. Okay, so y values that I care about, not the order pair, not the x value. Okay, any questions? Okay, let's go to page 7. I'll do page 7 with you, but I'll also do this in class as well. Okay, so we're going to do this twice. Okay, once here and then once. Okay, so this is something that I want us to make sure we understand is when you're applying or approximating a calculus process, your units of measure will change, okay? So anytime you do a derivative, your units will continue to increase their denominator units, right? So if it's ounces per minute, the derivative will become ounces per minute squared, right? And if you take the antiderivative, then your denominator units will be stripped away, okay? So anytime you do, even if it's approximating, that process is still going to happen, okay? Your units will always change if you force something into a derivative process or into an integral process. Okay, so hot water is dripping through a coffee maker, filling a large cup with coffee. The rate that the rate that water in the cup at time t is changing is given by a differentiable function, c of t. That just means a smooth curve, okay? No breaks, no sudden changes. Since we can't see the full graph in front of us, they kind of have to tell us some basic behavior. Select values of if c of t measured in ounces per minute. Okay, so c of t is already a rate, okay, given the table above. Okay. So we see that at 0 minutes, water in the cup hasn't started yet, but then at 1 minute, water is coming out at a rate of 5.1 ounces per minute. And then 3 minutes, it's going to slow down a little bit. It's only going to come out 4 ounces per minute, so it's not coming out as much. And then 6 minutes in, 3.3 ounces per minute, 1.2, and 2.3. It's on this. Yeah. So one's about theta and one's about that. Okay, interpret the meaning of C prime of 6 and indicate the units of measure. Okay. So we know that C of t is already ounces per minute, so we know that C prime must be talking about ounces per minute squared. Okay. So we know that this is already the rate that the water is coming out. So basically your C prime of 6 is going to tell us the rate of change of this rate. Does that make sense? Okay. It's the rate of change of C of t. Right. So we see that the rate of water is ounces per minute. And so C prime is going to be how fast that rate is changing. At 6 minutes. And it says indicate the units of measure. So units of measure is going to be ounces per minute squared, ounces per minute per minute. Okay, approximate the value of C prime of 6. So we can't do calculus, we can't do derivative. We only have a table of values, so the best thing that we can do is what? What's another word for derivative? Okay. Derivative is just a fancy word for what? Slope. Yeah, we just find slope. Anything around this region is good. Right? I can pick any order pair, and that will give me slope. Right? It just says approximate, so we don't have to be completely accurate, but we do have to at least know that our best chance of accuracy is around the source. Right? If we're choosing over here, then we're too far away. We want to be close to the source. So I'm going to just choose 2. I'll choose these 2 points here, but you can choose any of these 3 points is sufficient. Okay, are you okay so far? And also, we have to make sure that we describe what's going on. I think the tendency is it's easier for us to say things in terms of like velocity or acceleration, but here it doesn't fit the context of this problem, right? We can't just assume, oh, second derivative is acceleration, and we say acceleration when that's not really, it doesn't fit this problem, right? There's no acceleration going on with the scenario that we have in front of us. Okay. All right. So now part C, interpret the meaning of the definite integral from 1 to 10 of C of t and indicate the units of measure. Okay. So we know that the definite integral from 1 to 10 of C of t means that we're changing the ounces per minute to be ounces, right? And this is really applying first theorem. Okay. We know that C of t is ounces per minute. If we take the antiderivative, it'll turn into ounces. So imagine we take the antiderivative and it becomes uppercase C to indicate that this is now ounces per minute. So the way that we indicate displacement, what's really happening here is that this is indicating the change in the amount of coffee in the cup between the 1st and the 10th minute. Okay. Because between 1 and 10, right, water will keep accumulating into the cup. And so what's going to happen is if we take the antiderivative, we're accumulating all those rates, and we're going to be able to tell exactly how much change is there in the cup in terms of the amount of water. Or, sorry, water going into the coffee maker, which is producing the coffee. Okay. Between the 1st and 10th minute. So we know that we're starting off with ounces per minute. If we take the antiderivative, we're going to strip away that denominator, and it's only going to be in terms of ounces. So now part D, we're going to approximate using two middle rectangles, okay, between 1 and 10. So we're going to go ahead and do what we did on the quiz, where we separate into two subintervals, right? We always go from the middle of the order pair to the middle of the order pair of the next one, and then we are always going to overlap with the previous interval. Okay. So two middle rectangles here, 6 minus 1, that's a width of 5. 10 minus 6, that's a width of 4. So now we do width times height. 5 times 4.2, 4 times 1.2. All right, notice our units changed as well. So what that 25.8 tells us is that roughly, okay, this is just an approximation, but roughly 25 ounces of water got added, or coffee got added to the cup between the 1st and 10th minute. Okay, that's what this is telling us. So this is a very popular type of AP exam problem where they give you a scenario, they give you a rate, and then they're asking you if you can go through and tell them about the derivative, tell them about the antiderivative, and be able to explain what it is in terms of what's happening in the problem, right? And we don't want to use the words velocity or acceleration, right? It just doesn't apply to this problem. Okay, part E, approximate the average rates of water being added from 1 to 10, results from D. Okay, so this is average value theorem. Okay, let's adapt it for part D. So basically, it's part D with a fractional value in front. Now, when we take the antiderivative, we're going to end up with 25.8 ounces. Right? But then that 9 is basically we're dividing it by time, so it's ounces per minute. So it's going to go back down to ounces per minute. So even though we took the antiderivative, we did make our way up to ounces, but then that divided by 9 is in terms of minutes. So it's taking us back down to the rate, which is in the same units as these here. And that's what we want, right? We want the average rate that the water is being added. The average rate is ounces per minute. Okay, so on average, between the first and 10th minute, there's an average of around 2.8 ounces of water added to the coffee maker per minute. Yeah, it's over there. On my, yeah, there's 2 of them. Okay, any questions? Okay, so we're going to pick this up in class and then help session tomorrow morning as well.